welcome back to the pycse channel. Today I want to talk a little bit about linear regression and a couple of different ways we could approach what we need to do. So linear regression is shown schematically in this figure, and what it means is the model, the data points, the y here, is a linear function of some parameters. And that's expressed in this set of matrix equations here, where for each one of these points we have say 1, x, and x squared, and we multiply by p0, p1, p2. So you can think of that as a dot product, and that gives you y0. So that's linear algebra. This output is linear in the p's, and the goal is to find the best set of p's that minimize the error in our fit. So we have more data points than we have parameters, and so we cannot solve it directly, and we have to think about it in some least squares fitting approach. All right, so that's what I want to look at, a couple of different ways to do that today. So let's start with some data. This is some data, concentration versus time, from, say, a chemical reaction, and it starts out at 0.05 and it goes down. And our goal might be to fit a function to this data so that we could make predictions about where it's going to go. So we can do that if we just choose a polynomial fit as the simplest. Let me make sure I run this. If we choose a polynomial fit, we can just use polyfit, and I've talked about that before. So let's have a look at np.polyfit. We have some data, some y data, and we have to choose what order of polynomial we want. So this is obviously not a line, but let's go ahead and choose a first order polynomial so we have something to look at. And I should not name this, I should name these what they are. And now we get these two numbers that come out. And to remember what these are, we have to read the documentation. So let's see. The polyfit does a least squares polynomial fit, and the p0 is the highest, so this is the slope and the intercept. So the constant term goes at the end. All right, so let's take a minute and plot this so that we can see what our fit looks like. It should make sense. The slope here is negative. This line's going down, and we could say plot time comma ca time comma np dot polyval p comma time, and let's make that a red line so that it's easy to see, and I'll go ahead and put a legend. Okay, so let's see, that does not look good. Maybe this is backwards. I should have read that detail too. Okay, so it's still negative, and now it fits when we do things the right way. Now, it's obviously not a good fit. It is underestimated here, overestimated here, and underestimated here. But it's now easy to make this a 2 and fit a second order polynomial. And that one looks a lot better. We could go to a third order, and a third order looks like it fits pretty well. And you can't really ask for much easier fitting than this. These are literally giving us the coefficients of this one is third order, so this would be time cubed, time squared, time, and the constant term. So let's take a couple of steps back here and see how we can, what are the limitations. One of the limitations is you have to have all of the orders. So there is no way to eliminate the linear term or the quadratic term. You have no choice but to include them, because that's what polyfit does. And if you knew that these should not be here for some reason, then we need a different approach. So we'll talk about that. Different approach in a couple of steps. The next thing is we use polyval, which is a really convenient way of evaluating at different times for making predictions, but we'll look at in a moment how we could do this ourselves. All right, so we have P, and let's look at np.polyval of those parameters, and let's pick a time of 250. All right, this gives us a number, 0.01976, and the question is, where does that number come from? And that number comes from a dot product that I told you about. So I'm going to say t equals 250 here, and then let's do np.array, and we'll do 250 cubed, 250 squared, 250, and 1 are the constants, and we'll do a matrix multiplication of that with p, and that should give us that same exact number. And it does, plus 1 extra decimal place, it looks like. So this is exactly what is happening when we are using polyval. It is constructing this, doing this matrix multiply with p, so that we have this times the first coefficient, this times the second coefficient, this times the third, and 1 times the constant. And we can do this for all of the time values. So I could write time cubed, and it will give me each time step cubed. And I could write time squared and get those, and of course we can just have regular time, and to get the ones we can take everything to the 0 power and get the constants. So if we had a way of constructing the columns that I illustrated here, I wrote these in the opposite order, but the p's would then be in the opposite order, so it doesn't really matter. What we need is to construct these times in columns. So an easy way to do that is to start with a list. Let's do time cubed, time squared, time, and this. So this will be like a list of the four rows. And we should make this, let's make it an array, np.array. And it is in row shape now, and all we have to do is transpose it, and we get the columns. So here I have the ones on the right. Here's the time squared, and time cubed. And now I can multiply this by p, and this will give us the predictions for each one of the points. So you can see here we start out at approximately 0.05 and end around here. And if we subtract y from this, this will be, I guess this should be CA, this will be the errors associated with our fit. All right, you have to remember a couple of things. One is the exponentiation happens at a higher priority, and it's inside these parentheses, so this all happens first. Matrix multiply is a higher order operator than minus, and so this whole thing here gets evaluated first, and then we subtract off the CA, and that's an element-wise subtraction. All right, so now we are getting close to where we could start to think about what if we wanted to get rid of one of these terms. Like, we don't want a constant term because we know it's going to go to 0, for example, or we don't want a linear term, or we don't want one of these. So we can start to do that, but we have to move away from polyfit. And the next thing we'll look at is np.linalg.lstsq. All right, so np.linalg.lstsq. So this is a function that computes the vector x that solves the equation ax equals b in a linear least squares sense. So back up to our picture here. This is the a, the big thing that I called x here. And then b is the known y values, and x is the parameters that we are searching for. So if we can construct the a and the b matrix, then we have a one-line solution to get our parameters. Okay, so I showed you that the x array is just going to be like this, and there are lots of ways to make this, but I'm going to stick with this for now. So let's make that there, and then we just have to call np.linalg.lstsq of x, comma, ca. And this should give us a, oh, doesn't look good. Oh, this is just an old warning. Let's say our condition equals none. Okay, so this is returning a couple of things. It looks like I should have paid attention to what this returns. So it returns x, which we want, and the residuals, and the rank, and the s. So it returns a lot of information. So let's put in, I'm going to call it pars instead of x, residuals, rank, and s. And we don't need any of these. We're not going to look at them, so actually why don't we just make them underscores to indicate that we want them, but we're not going to use them. And then let's say what the pars are. Okay, so these parameters now are exactly the same as the parameters that we saw before from polyfit. Let's see, here's an easier way to see it. So you can see we get exactly the same parameters in each one. And here we've used this np.linalg.lstsq. Now, why is that especially helpful? It's especially helpful because we choose which columns that we put in here. So if you want to get rid of this one, we can. And we'll have one fewer parameter. And let's go ahead and plot dot plot. Let's see, time, comma, ca, comma, let's make this blue circles, and time, let's do x at pars, and make this a red line. All right, so there you see we get a different kind of behavior that levels off over here, and it's not necessarily a better one, but we can make this be to the fourth. In fact, you can make any function in here you want. We could even do time to the 1.2 if that was something that made sense. And that remarkably looks really, really surprisingly good for just guessing at 1.2. All right, so that's the benefit of linear regression. Unlike nonlinear regression, we're not making any guesses here. We are directly solving for the parameters and doing that in a least squares sense. Now this least squares sense, we could also go back to the normal equation. So let's see if we can work out what that might be here in a couple of steps. So what we had in our formula is that we had an array x times this unknown p is equal to y. Now these are not square, so remember that we have some like long, tall thing for x and a little thing for p, and that's equal to some long, tall thing for y. Now, since we have more equations than unknowns, we can't exactly solve this as an ax equals b unless we do some algebra tricks. So the algebra tricks look like this. Let's multiply each side by x transpose. Right? This is just the linear algebra equivalent of multiplying each side of the equation by the same thing, so we haven't changed the equality. And now let's further multiply by the inverse of x transpose x. All right, seems like we're making a big mess here, but this whole thing here is equal to the identity matrix by definition, and so we can just kind of eliminate it, and that gives us now an analytical solution for p that is x transpose x inverse times x transpose times y. Now, this is something we normally only do on paper or on the screen here to illustrate how it is possible to evaluate the right-hand side. The inverse is a tricky operation in general for large systems, and that's not how we actually do the calculations. But let's work out what it looks like for us in Python. Okay, so the formula that we ended up with was something like P equals X dot transpose at X raised to the minus 1 times X dot transpose times Y. All right, so that's what we need to evaluate. All right, and we are going to stick with this X, so let's put our pars here for reference. All right, and now we want to evaluate this right-hand side over here. So the way we write that is np.linalg.inverse of x.transpose at x. So that's the inverse of x transpose at x, and then at x transpose, and then at y. So this is the matrix multiplication that should give us the same 3 parameters. And this should be CA. I'll probably only do that like 2 more times in this video. So this is just the analytical solution that the linear least squares is giving us that I kind of stated without proof. And the only thing that it relies on is that x transpose x has an inverse. That is, it's not singular and it's well behaved. That's another topic for another day of what those words mean. But here we have a nice expression for the analytical solution that we get from what was wrapped up inside the linalg.least squares. Okay, let me wrap it up with one more critical concept, and that is in engineering, when we do regression, we often want to know how confident are we in these numbers. And you should be suspicious that you see this really small number and a comparatively bigger number. That are these really relevant? And that brings me to the pycse.regress. All right, so let's take a look at it from pycse, import regress, and let's see what it says. All right, so regress is going to build off of the least squares function and provide confidence intervals that account for the sample size using a student t-multiplier. So it's a lot like the nlin fit code for nonlinear regression, but it is for linear regression. And so we use the same idea here. You create your columns. I use column stack here, but we'll use the X that I already created. And you give it a value, a vector of values you want to fit. You choose a confidence level. So for 95%, it's 0.05. And then this will give us the 3 things that it returns are the fitted parameters, confidence intervals, and the standard error on each parameter. All right, so let's do that. So we just type regress, X and CA, and I'll be specific 0.05 here. And let's do RP, RPCI, and SE for this. And first, let's make sure we get the same parameters. So RP, this is a warning that we can ignore. RP comes out exactly the same. And let's look at those confidence intervals now. I call that RPCI. And this shows us that we have confidence intervals that are the same sign for all 3. So this does not cross 0, this does not cross 0, and this does not cross 0, which is an indication that these are 3 important parameters that we cannot further eliminate to simplify our model. All right, so that is the end of what I wanted to look at in a bunch of different ways today, thinking about linear regression, how it is normal linear algebra. You can use polyfit if you know that you want a linear polynomial. You can use np.linalg.lstsq if you want more control over which columns you use. And you can use the regress function if you want to have confidence intervals on those parameters. All right, that is all for today. Thanks for listening, and I'll see you next time.